Okay. Okay. So today I'll give the
I think we're going to start recording. So Luyan, could you start recording? Yeah. Yeah, go ahead, Gumi.
Yeah. So today I'll give the paper. I'll lead the paper discussion on Fe3 plus partitioning between clinopyroxene and silicate melt at 1 to 2.5 GPa. Implications for iron, ferric iron content of MORB and ocean island basalt source mantle. So this paper is authored by Abhishek Rudra and MORB and Hirschmann. So Abhishek Rudra is a postdoc at Planetary Chemistry Group of University of Cambridge. So he did his BSc from Presidency College, Kolkata, and his master's from Indian Institute of Technology, Kharagpur. Then he did his PhD from University of Minnesota, Twin Cities. Mark Hirschmann is his professor. So he is currently a professor in the Department of Earth and Environmental Science, University of Minnesota, Twin Cities. And he did his master's from University of Oregon, PhD from University of Washington, and postdoctoral from Caltech. So, the main objective of the paper was to find the iron, like ferric iron partitioning between pyroxene and silicate melt at high pressure pressure condition and at a high aluminum bearing melt. So earlier, Abhishek Rudra had a paper in 2021, which was also on the clinopyroxene and partitioning of iron and pyroxene and silicate melt, but that was at a lower pressure condition. So this is at a higher pressure condition and with a higher aluminum concentration. So if we see the starting composition, so the aluminum concentration is more than about 9 weight%. And these are the main experimental conditions that has been set. So we can see that the temperature condition is also closer to 1300, 1400 degree centigrade. And according to this particular study, so actually the Fe3 plus concentration in the upper mantle, that can this constraint of partitioning coefficient can help in understanding the redox condition of the upper mantle, and that would help if we have an idea of this peridotite Fe3 plus by Fe total ratio. So that would help understanding the diamond carbonate melting depth as well. So these are the already predefined curves. So according to this particular study, if we see, so the decarbonation melting that commences at about 150 kilometer beneath the regions. So if this ratio is constrained properly, so these melting nature of melting or partial melting can also be constrained in a better way. So as I had mentioned, what are the conditions of the experiment? So two buffering redox buffers have been used. So the buffer that is used is I forgot the elemental name. So this is the buffer that has been used. So it has a higher oxygen fugacity compared to the upper mantle condition that they have attempted. So the closer oxidation, the FO2 condition is represented by the iron platinum alloy capsule. So this is the capsule within which the experiment has been done. And they have taken andesite melt because the clinopyroxene is the only crystallizing melt at that condition. And therefore, they could crystallize large grains of clinopyroxene, and these grains are not zoned. They are quite large. So they are about 80 to 100 micrometers. So analysis can be done easily on these. So they have established that the samples have been homogenized. So they have like reached the equilibrium, and like the QFM they plotted it from the Fe titanium alloy and from the glass, the Fe3 plus by Fe total concentration of the glass. So this they plotted by existing empirical equations. So if you see the plot almost fall on the 1:1. So because the FO2 condition of both are equilibrium condition. Also, the slow diffusing ions such as titanium and iron, they have almost a similar or a profile all along the clinopyroxene green. So that also suggests that it has properly equilibrated. So
So wait,
after
let me explain a little bit here. Since that, yeah, the previous slide, number 4.
Yeah.
Okay. So for, I don't think everyone has done experiments here, but I could explain a bit more. So what people did was that, okay, you see the bright part in the images, the bright part. So that's a ruthenium oxide. So basically it's a ruthenium as a metal. So people use this certain type of metal like iron, ruthenium, or gold. So then you wrap a sample inside. The wrap sample here are the silicate, which is a sort of like say andesite composition. So andesite supersonic, I didn't hear it. And what you get is that, okay, you use a metal to trap something inside, then everything is closed inside. So then you do the experiments, let it equilibrate, hopefully. So after you equilibrate, people could write different reactions. For example, for the iron platinum. So after concentration, for example, you have 80% iron, 20% of platinum, or something like that. And then the iron platinum, there is a two end member mixing thermodynamics that are relatively well defined. So that by that, people could calculate the iron activity in the system. So iron activity based on the iron concentration of the iron platinum alloy that people measured. And through iron activity, and people could calculate the oxygen fugassity through the iron plus oxygen forms the iron oxide reaction. So that standard reaction has been very well calibrated. So this is the way that people could do that. And then another way people could calculate is that you look at the glass, and in the glass you have Fe2 plus and Fe3 plus, right? So you have the iron 2 plus, add oxygen, and you form iron 3 plus. So something like this. I didn't match the numbers perfectly, just to show you the idea. And for this reaction is also well calibrated. So people could use this to calculate the activity, oxygen fugassity, which is basically the activity of oxygen in the system. So that's how it works. And the samples are very small, as you can see here. It is at several centimeters. That's how it is when people push for very high pressure, high temperature conditions. So the small sample wrapped by metal, and you have the silicates, and then you have different phases precipitated. And that's how people understand the thermodynamics in high temperature, high pressure conditions. So Urmi, go ahead.
Yeah, so they did first they started with the EPM analysis of the glass and the clinopyroxene grain. So they observed some and from that calculation, what they calculated is the partitioning coefficient between the partitioning coefficient of Fe3 plus between the clinopyroxene and melt. So after they calculated this, they made some plots, and what they observed is that as expected, they got some positive correlation with the oxygen fugacity. So we can see that this partitioning coefficient has a positive correlation with the FO2, like QFM, del QFM. So del QFM is the difference of between the oxygen fugacity condition and the like FO2 of the QFM at that condition. So we can see that this is a positive correlation. However, if we see these particular points, so they have a very opposite trend. So this suggests that oxygen fugacity is not the only controlling parameter of the partitioning coefficient of Fe3 plus between clinopyroxene and MET. So when they plotted these the partitioning coefficient with respect to the aluminium oxide concentration of the clinopyroxene, there they found a positive trend. So this suggests that the Al3 plus and Fe3 plus substitution is dominant in this case, and therefore with the increasing aluminium concentration, the Fe3 plus concentration is increasing in the clinopyroxene. And they tried to regress it with this particular equation, and this it has a comparatively good fit. Also, they tried to compare the they made some regression equations. So these are the two regression equations. So first, what they tried to do is they plotted experimental Fe3 plus partitioning value and this predicted Fe3 plus partitioning value using only aluminium concentration of clinopyroxene and as a variable. So we can see that in this case, the R square value is about 0.58. And when they included the Fe3 plus iron oxide, Fe2O3 component of clinopyroxene in this regression equation, there is a slight improvement. That is from 0.58, the R square value changes to about 0.68. So there is a little improvement. However, it indicates that the control of aluminium oxide in the clinopyroxene structure is very important, and it has a good effect on the Fe3 plus incorporation or the partitioning value. So here the different these are the experiment these are the values that have been experimentally determined, the partitioning value from this particular experiment, and these gray points, they are experimental values at a lower temperature, like lower pressure condition, that is about 100 kilobar. So these are at about 100 kilobar, and these are at about 1 to 2.5 GPa. So we can see that with pressure, there is an increase in the Fe3 plus partitioning value of clinopyroxene, and so between clinopyroxene and melt. So with pressure, this value increases. So also they have plotted two reference values. So this is this particular reference value that has a very high Fe3 plus partitioning coefficient. So it is of a very highly aluminous clinopyroxene composition. So here you can see the aluminum composition is quite high. So for this particular paper, so this suggests that increasing aluminum concentration can increase the partitioning value of Fe3 plus. So what they did is they plotted various experimentally determined Fe3 plus by Fe total concentration in clinopyroxene. And these are the these triangular points are experimental data, whereas these circular points, they are sample data. And these are from the spinel peridotype, and these points, they are from the clinopyroxene garnet peridotype. So, and here what we can see is the color bar that expresses the aluminium oxide concentration. So these clinopyroxene and garnet peridotype, they have a very quite low aluminium concentration compared to these. And possibly the reason is because garnet preferentially fractionates aluminium. So here what can be observed is, if we take similar kind of data, so as expected with increase in oxygen fugacity, there is a positive trend, like the Fe3 plus concentration increases with a change in oxygen fugacity, which is true for all the three type of samples, although they have different slopes, and they cannot be we cannot compare them together. So the possible reason, one can be the difference in pressure, temperature, or aluminum weight percent, like concentration of aluminum. So because as we can see that the aluminum concentration for these sample data, they are quite high compared to the experimental data. And as earlier it has been established that increasing in aluminum concentration increases the Fe3 plus incorporation in the garnet, in the clinopyroxene. So that can be one reason. However, we can see that it cannot be explained only by aluminum concentration, because in that case, these points would have also followed a particular trend, but they do not. So there are multiple factors that control these partitioning, like Fe3 plus by Fe total incorporation. So they are like other factors like pressure and temperature. Temperature also has role to play in this. So in this paper, what they have done is they have tried to use the existing thermodynamic software, so example PMELS and Perplex X, to plot the Fe3 plus partitioning coefficient in clinopyroxene and melt at different like oxygen fugacity condition. And what they can see is that both these thermodynamic models, they overpredict this partitioning value. So the possible reason, like for example, if they compare the PMELS, so this has a very high deviation. So the possible reasons can be that one, they have used the EPA, the stoichiometric reconstruction from the EPMA analysis. So the Fe3 plus they have calculated are from the EPMA analysis that have been stoichiometrically constructed. So these values might differ from the actual MOSBA data. And also the clinopyroxene grains, whose thermodynamic properties have been used in this model, they are compositionally zoned. So possibly equilibrium has not been attained in these cases. So therefore, there is a large deviation. Although the Perplex X data, so they have like some similarity with these experimental value, but even then, we can see that they are quite a few magnitude different from the experimental data. So as from different plots, it has already been established that with the increase in the oxygen fugacity, the Fe3 plus concentration is increasing. So they have suggested these two equations, which suggest that this increasing oxygen fugacity can cause a replacement, like these substitution mechanism. So here, aluminum is being substituted by Fe3 plus. So this reaction 12 can be one of the reaction that is possibly operating in this condition. Also, by these thermodynamic calculation, they found that at MORB situation, so with a change in the sodium concentration, that is Na2O value, when the oxide concentration of oxide value of sodium increases, and it shows a negative correlation with the Fe2O3 value. So they have tried to plot it using these softwares, and that possibly has a relation with the progressive crystallization and exhaustion of some particular phases, for example, phenyl and clinopyroxene. So this part I'm not very clear, because I was actually like saturated by the time I reached this part. So however, when they also like made some corrections for like olivine crystallization and all, and finally at different temperature condition they plotted these and these are the different F values, that is the fractional crystallization value. So for that they plotted the the evolution path of the Fe2O3 and sodium oxide. So they calculated the source peridotite Fe3 plus by Fe total value from the all MORB data that are available, and what they found is majority of the peridotite composition, almost about 75% of the MORB data, they give a source peridotite FO2 Fe3 plus by Fe total value of 0.038. So most of the values are above this range. So they also calculated this Fe3 plus evolution at a different pressure condition. And here they have compared them with the different available Fe3 plus by Fe total value of different MORB and OIB samples. So here what they have found is some of the OIB, so they have a very high Fe3 plus concentration. So some of them, like for example, in case of Hawaii and Iceland, they can be explained by it is not essential to explain their high Fe3 plus concentration by a enriched source, because other factors such as temperature and pressure also plays a role in controlling the Fe3 plus concentration. So at a greater depth, if partial melting occurs, so in that case, a very less amount of partial melt will form, and with the Fe3 plus behaves as an incompatible element, so that will preferentially fractionate into the melt that is formed at a high depth, and therefore the Fe3 plus concentration in the particular melt will be very high. So in case of Hawaii and Iceland, this Fe3 plus concentration can be explained by the fractional melting and by the partial melting. However, for other composition, for example, the Canary and Cape Verde, so here the Fe3 plus concentration is quite high, and this for this some enriched iron Fe3 plus enriched or source has to be possible explanation. That could be the possible explanation. So overall, what they have summarized is that at the whole experimental range of about 1 to 2.5 GPa, and at about the oxygen fugacity spanning from about del QFM value from 2.7 to plus 5.1 range. So the Fe3 plus the partitioning coefficient of Fe3 plus between clinopyroxene and liquid, the value is ranges between 0.05 to about 0.81. And if the pressure is fixed, this value would increase with increasing FO2 condition, and it also correlates positively with the aluminum oxide condition concentrations. So it also suggests that apart from aluminum concentration and FO2 condition, the temperature and pressure are also controlling factors. So as I had already mentioned, and it is also a summary, that the earlier thermodynamic models, they exaggerate the bulk Fe2O3 concentration in periodites, and they overpredict the Fe3 plus partitioning. And there is a negative correlation observed between the Fe2O3 and Na2 oxide as observed in the MORB. And so almost 75% of the data, MORB data, they give a similar Fe3 plus by Fe total ratio of about 0.038, and they are very similar to the continental lithospheric mantle, which also have a very similar composition. And the higher Fe3 plus by Fe total observed in some oceanic island basalt can be due to the incompatible behavior of iron in source regions rather than more oxidized mantle. And in other cases, for example, Canary and Cape Verde, in these cases, the possible reasons of high Fe3 plus concentration is because of oxidized source, and this source can be as enriched as about 0.068. And also melting effects can also contribute, but they have not quantified its impact. So these are the major conclusions. And for this particular study, they have used Zanes and Zanes to calibrate and to measure the Fe3 plus concentration in the experimental samples. So this is the calibration, and the calibration has been done based using the Mosby spectrometry data, and this is the centroid energy. So these are the reference curves that have been drawn based on the standards. And what is the centroid energy? The centroid energy, so area normalized centroid energy can be explained by this particular equation. So, and this is the final equation that has been used for calculation of the Fe3 plus by Fe total concentration. So this E value, this is the area weighted free edge centroid energy. That is this particular thing. And these are like coefficients A1, A2, A3, and mu. So they have been given in this here, what we can see. So if we try to understand what are these values, like centroid area normalized. So for example, this is a Zane's curve. So this is the output graph that we get after a Zane study. So this is the energy, increasing energy of the X-ray, and this is the normalized absorption curve. So this part is the Zane's absorption curve, and this part is the extended X-ray or like EXA-FS. So for our this particular Fe3 plus by like Fe3 plus Fe2 plus so or measurement of Fe3 plus and Fe2 plus, only this Zane's portion of the curve is essential, and mostly the calculation is done on this particular part, that is the pre-edge curve. So here, if we see, this is the entire spectrum and this is the pre-edge part. So if this part is zoomed, we can see that there are two particular peaks. And so after the background is like subtracted, so these are the two peaks. And then the calculation is done. So there may be multiple peaks. For example, here we can see two peaks. There might be three peaks. And so the centroid and this percentage of area of peak one and is multiplied with the centroid value. That is this this value of the centroid. So so based on that, this centroid area normalization, like area normalized centroid value is calculated. And that is this E that is incorporated in this particular equation to get the Fe3 plus by Fe total value. So that is what I had to explain today. Any questions?
Okay, thank you, Urmi. It's pretty good. Give us an explanation of Zane's. As mentioned earlier, in the previous discussion is better. I think this set a good example that to explain if there's analytical chemistry, then explain what the basics of chemistry, and then what equipment and people going to use for this, and how does this equipment generally work, some general principles, so that we can interpret the results. And similarly, for future readings relevant to other data related different algorithms, it's also good to explain to other people that what's the basic principle of that and how does it work. So I think it's pretty good. Okay, questions from our participants today? Hope everyone of you will read the paper.
I have a question. So can I ask?
Yeah, absolutely. Go ahead.
Yeah, I was pretty confused by the fact that how would change in the oxygen fugacity change the partitioning coefficient? Like, for example, partitioning coefficient, as far as I understand, it is mostly dependent on the structure of the mineral. Like, it is more dependent on the structure of mineral that is crystallizing. For example, like pressure temperature dependence, I understand that the the vibration of the sites, the site vibration increases. So, for example, at a high, like if the pressure increases, so the size of the cation site would decrease, and therefore aluminium 3 plus will be preferentially incorporated because size of aluminium is the cation size of aluminium is smaller compared to FeMg. So pressure dependence can be understood in that way, but like how oxygen fugacity affects this, like how the partitioning coefficient is controlled by oxygen fugacity.
So to me that it works in a different way, but with similar results. So when you think about the pressure, so you squeeze it, you change the size, affect the size. So actually for here for oxygen fugacity, it affects basically the ability of an cation here as an iron 2 plus and iron 3 plus to bond with oxygen. So the higher oxygen fugacity it is, then is it easier for I won't say it's easier. I mean, it will simultaneously affects both iron 2 plus and iron 3 plus to bond with oxygen in the crystal, as well as in the silicate melt. So, and then these two elements, when the oxygen free gas changes, they don't behave the same. So that's why the element with different valence states, for example, iron have iron 2 plus, iron 3 plus, vanadium have vanadium 2 plus, vanadium 3 plus, and vanadium 5 plus. For these elements, their partitioning coefficients will be sensitive to the change in redox, because in the crystal and in the melt, these two are different valence state. They have different bonding ability or bonding energy with the oxygen. So when the oxygen free gas changes, of course, it is expected that they should change. So that's my interpretation for it. So could you go to that slide that they have the P melts as a perplex modeling?
This one?
I think they have, yeah, slide 8, I think.
Yeah, so this is for the females and the perplex.
Oh, sorry, I was up. So I think for this one, so to me, when I look at this work, I think that's the I wouldn't say it's the take-home message, but let's say this highlight that I want to make in this paper. One of the most important one, at least as I think, is that they're going to say, okay, so because when people do all this thermodynamics, you measure different equilibrium. For example, here they measure the equilibrium of the clinopyroxene and the melt. So they basically change the thermodynamic parameters people use, because otherwise, for P melts or purple X, which are the thermodynamic software people use to solve the thermodynamic equations. So let me explain you more about this, because maybe some of us in this room haven't used this before, or don't know that how this P melts or purple X works. So for them, I don't know what exactly the words of this, but let me just write in this way. So basically, then you have the silicon melt. So you have the CPX silicon melt equilibrium. So by different elements, for example, you may have the iron or magnesium. For example, let's make it easy. That's normally something you will do. So you have the iron magnesium exchange between these two phases. So one phase is a silicate crystal, silicate solid, clinopyroxene solid. Another phase is a silicon melt. So you have these two phases equilibrium with each other. They have exchange different elements. Okay, so it could be iron 3 plus 2, iron 3 plus or iron 2 plus. So then, as you change the oxygen fugacity, and then you are going to change the equilibrium. And so basically, for this system, for example, if you fix temperature and pressure, you only evolve the oxygen fugacity. So if we assume it's a closed system, then with every oxygen fugacity, then you are going to recalculate the equilibrium. So that's how this software goes. So here they choose 1, 2, 3, 4, 5, 6, 7. They choose 7 black points, black squares, and 7 blue stars. So these are 7 modeling results coming from the software. So they solve the thermodynamic equations by 7 times. So each time they solve it, they come out with a result. And this is also widely used for magma cooling or partial melting. That basically you decrease or increase the temperature. So each time you increase temperature for 5 degrees, for example, and then you solve the thermodynamic equations, of course, you end up with different melt composition and different CPX composition, for example. And then, and then you also change the different proportion of the two phases, because higher temperature it is, the higher phase proportion for the melt it is. That is just mass balance. So basically for this software, they could help us to solve the thermodynamic equations iteratively. So step by step. So that's how it works. And here, but each time when they solve the equation, they use certain thermodynamic data from the thermodynamic database. Basically, that is a heat capacity, compressibility of different minerals. People have been measured before, as well as the let's say the different chemical mixing models that people have been used or measured, because it's always a multi-component system. So basically for this work, they show that, okay, neither purple X or P melts have the right thermodynamic parameter to calculate this, because it doesn't agree with that. It follows another trend. So for Urmi, could you point out that where is this, like, let's say, from your perspective, where does those differences coming from?
They have,
yeah, I don't know what in the paper they point out. So yeah, PMELs over predicts the ferric iron partition coefficients, but it must be somewhere in the equilibrium that something is wrong. So is that this equation 11, equation 12 they refer to?
No, these are the equations they use to explain that why this aluminum concentration is increasing. So they just explained it by by these two reasons, that one is the P melts, they take the EPMA Fe3 plus concentration of the clinopyroxene. That is up from the EPMA measurement, they calculate the Fe3 plus concentration by stoichiometric reconstruction. So and that might differ from the actual Fe3 plus concentration. So that can be another one reason. And the second reason, what they mentioned, is that the clinopyroxene grains that have been used for the thermodynamic calculations, in the data, so those grains were compositionally zoned and possibly the equilibrium was not attained. I can just go to the paper also. The part. Hello?
Okay. So okay. Okay. And by the way, yeah, Urmi, another thing I forgot to mention about to your previous question. By changing oxygen fugacity, basically you could change the site that both iron and aluminum sits, because they're different size. not only in clinopyroxene, but also in more heat discussion nowadays in bridgemanite, for example, the iron, aluminum could sit in. And then once you change the oxygen acid, they have different preference of sitting on different sites. So so some people that measure and study the partitioning coefficients of aluminum in different crystal sites. So that also involved with oxygen acid. So here, actually, they didn't give a quantitative answer to what I was asking. So y is different than so y purple X and melts so the over-reciprocate the parting coefficients. Actually, I have another question to this, but let's first look at Trentow's question. So he's asking about the oxidation of the arc of magma. They still debated that the oxidation of arc magma in Harris is source or results from being oxidized during magma ascending. So whether it's a source or is during the ascending upwelling process that causes oxidation. So the oxidized state of arc magma, for example, indicated by higher iron oxide values. So that's what people have been being used, including different element ratios, may similarly be caused by difference in melt composition, as this paper presented here, not due to the oxidized source of arc magma aluminum conduct. Yeah, I think this is actually it's interesting because when Abhishek was pursuing his postdoc, this was a work that he was doing his PhD. He was trying to do some iron isotopes on this. But it's not easy to do because for iron isotopes, if you dope in the system, it's very complex because you wrap the samples with the iron platinum. So basically that will also affect your iron isotope fractionation. So it's a little complex for that. So for the experimental stuff, but I do think that it is it is a good approach for that. So to me that as an echo to what the Trentau person showed here in the chat. So Urmi, could you move to the slide where they have the horizontal axis of aluminum concentration, aluminum oxide concentration, and vertical axis of ferric iron concentration?
This one. This is actually the partitioning value, like a D value.
Yeah, the effects of aluminum concentration on the partitioning coefficients of iron 3 plus between the two bases. Sorry, my internet is a little bit unstable, so the slide has not shown up yet. Okay, I see one. Actually, when I see it, I say, okay, this is making what the Wei-Hua Huang's presentation more interesting, right? So Wei-Hua Huang, like I said, worked with us that published a paper in American Mineralogist. So in his work that he predicted that iron 3 plus according to the major elements. So concentrations. So basically for the experiments, if it is controlled experiments, then you have input of temperature, pressure, and also oxygen acid. So you will have that. So when I look at this, I see something that is very different. So okay, although they draw this line looks like this, so you don't look at please don't look at R square or RMSD. So you only follow the symbols. So as far as I could recall, so we'll move to slide 5. I think do they have the caption for that?
This one?
Yeah, okay. This one is good. So you can see that the purple triangle is 1 GPa result, right? So you can see that, okay, they don't really follow that line. It's a little bit strange. So they come from, let's say, horizontal axis 2.2 weight %, and go 3-weight person, then going up. And then for the blue, basically is another curvature, looks differently, right? So it bend the other way as the 1 GPa result, as is shown here in this plot. And then 2 GPa, of course, is bending another way. And 2.5 GPa bends another way. Actually, it's not surprising to me, because to me that this is basically, they change the delta G of the system, the Gibbs free energy of the system, because they change with higher pressure, of course, the compressibility changes, and also it's a different temperature, so heat capacity changes. So you change the delta G, and you're going to likely change them. And I won't expect the aluminum oxide concentration have the exactly same effect at the different conditions, at different temperature pressure conditions. Of course, it has an effect, but it's not the only thing. So it's a little bit complex. So Urmi actually for this part is also relevant to your garden one, that we could think about red thermodynamic equation for that, although it could be a little bit complicated. But we could come out to say, hey, all the parameters people have now are probably wrong. You won't come out with the red result, like what the purple X and P melts plotted in their previous slide. And machine learning could play a role there, actually. So, actually, it's interesting. It's interesting. So, any other questions?
Just an observation, if you see this particular trend, this and this trend, this actually like with pressure, the Fe3 plus concentration increases and there is like slight curve. Maybe pressure has quite some role.
Sorry, I didn't get it. So what is the role?
And like here, if you see these lines, so this is actually plotting according to pressure. So the QFM is not actually playing a role, and Fe3 plus is just changing based on pressure. So this seems like the curve is running this way, but like in many places, the variation has a like this kind of trend, which is possibly due to the pressure change.
Yeah. I think then for the ruthenium, the ruthenium oxide, the buffered experiments here shown here have the negative slope. I think to my interpretation that the oxygen frequency is too high. So all the CPX, in the CPX, probably they have the maximum iron 3 plus already. They probably could not move further by that. So basically that is I would say they are iron 3 plus saturated. So this is as much as iron 3 plus they could have in this CPX crystal, likely. And so therefore, further increase oxygen frequency actually won't have much effect on that. So basically what you have is the temperature and pressure. So here, as shown here, there is the pressure, right? So that's my interpretation for it. But once the oxygen frequency is a lower, like a QFM plus 2 or QFM or QFM minus 1, in this range, then once you change the oxygen frequency a little bit, then you change the side of iron 3 plus. Let's say how much iron 3 plus goes to which side in the crystal as well as in the silicate melt. And then this has a larger effect than temperature and the pressure. Or yeah. And also they often change the aluminum oxide. If they change all the other elements, I think they're also going to see something differently, right? Because here they are trying to fix with a silicate melt composition. So could you go to the very beginning to see what type of the oxygen frequency, what's the melt, let's say starting composition they use? So actually, this is not too Mavic. Okay, this is interesting because if you look at OIB or MORB, the silicon dioxide actually is lower than that, right? So, Umi, could you remember what's the range of MORB?
I don't remember right now.
So actually it's about 50%, if my recollections are right. So more, so basalt for terrestrial basalt on Earth, in my recollection is about 50%. So we actually really put a more felsic composition than that. So it's like an andesite composition. For a very simple reason, because to do it too mafic, you could not quench the melt. So actually they do put andesite composition. That brings another interesting thing, is that if composition affects the result, including the partition coefficient, then andesite composition and the clinopyroxene precipitate from it cannot replace the CPX basaltic melt equilibrium, which should be the real case in the Earth, right? Okay, but we could also ask this question to Abhishek on Wednesday. I think a question that's, yeah, I'll ask him to answer. Anything else? So could you move to slide number 5, please?
Yeah. Yeah, actually, that is also like, yeah. So these are at higher pressure compared to these. Like I think possibly it is that at higher pressure, the clinopyroxene incorporates more amount of aluminium because of the structure change. So that is why, like at a higher pressure, the aluminium concentration increases and the aluminium like iron substitution reaction occurs. So this is actually dependent on pressure also.
Yeah, I think so. So for this, they won't get very low aluminum concentration in the CPX at higher pressure samples. Yeah, aluminum will acquire more aluminum in the system, unless you really start with a system with no aluminum, or very, very, very little. Yeah, because in the system, the CPX precipitate is still a minority. It's not a majority, right? So it's only small amount of CPX precipitate from the silicon melt. Yeah, is that an explanation in the paper? Umi?
They have
as
not
well
they have not actually correlated the aluminum with pressure in the paper. So they said that pressure is one reason, aluminum is one reason, but they did not try to correlate both of them. At least I did not find.
But I think there is a bunch of paper there that explains the increase in aluminium in clinopyroxene structure based on pressure. I think you can find it in normal barometric situations also.
No, so this is possibly the explanation, but like in this paper they did not use this explanation. Okay.
Okay, I think that's another good question to ask Abhishek on Wednesday. Yeah, it's interesting because I know that people know that of the tetrahedral sites for the both aluminum and iron evolve with the pressure. That's something that people have been doing for a while, in not only in the mineral but also in the silicate melts. Okay, Urmi, could you turn to page 8 again? I think page 8 or page 9.
This one?
Okay, so my question that the P-mels and the Pro-X, page number 8. So I don't think that I will see how Abhishek answer that, because my understanding is that, okay, for P-mels and the Pro-X is the P-mels, like the melts was developed in the early 1980s. And the Pro-X, I don't know when, maybe slightly later, maybe 1990s. So it's a very old software. So they are like closed box. They solve the thermodynamic equation iteratively, but they don't let you know which parameter they use for a specific step. They only give you the output of the result, other than they trace to the thermodynamic database. So I think that's some shortcoming it has for all this classic software. I see there's a reason, because it's designed in those way. Also, they minimize. At that time, they have the limited computation capacity, and also they have limited, let's say, storage place. So think about in 1980s or 1990s, people were not use U-disk or laptop as what you are and me working now. These are really super computers back then. Even we are more powerful than supercomputers back then in 1980s and 1990s of university. So people use those flipped flop disk. So those, I say, very naive ones, if we're looking back to it. So back then, the codes were really designed those way. So trying to minimize computation capacity and trying to minimize the storage space. And meanwhile, it minimizes some information that we miss, and you get rid of some necessary information that actually we need sometimes. So I do think that we need to put this in the Python framework and then incorporate it into our geochemistry Pi as we're developing. That's what this Arthur Sahu is going to do in his PhD, and also that's part of the work that Wenyu is going to do in her PhD, working with me. So we need to put some this part, make it open, so that people knows the reason. So I will ask Abhishek for it, but I'm afraid that he doesn't know for it. It's not that he doesn't know, because the software doesn't let him know. So that's my so set predefined activity models. Yeah, but in each specific step, we need to output all the parameters. And we also need to know the range of the thermodynamic model that is reasonable, because for CVX, people measure from certain temperature, pressure, for example, and then we also make sure that for every calculation people have been used, it is interpolation rather than extrapolation.
Also, another thing, I think this particular perplex model is a new one. So the reference is of 2015. So this is possibly a modified version of the earlier one.
Yeah. They are constantly updating. I mean, for both of this stuff, people are still working on them. There are still people who are dedicated on working on this one too. They're widely used in the community. They're pretty good, but they're not open source. I mean, all the source code, you don't know. You don't know how to change them to fit your specific needs. We may have different needs than what the software designed. Okay. Okay, I think that's so much about today. And thanks, Urmi, for your leading the paper, and thanks everyone for your participation. So have a good day. Let's see the speaker on Wednesday. Bye-bye.